Hello everyone, welcome to the next lecture on the probability and statistics. Today we will discuss about the probability generating function. It is abbreviated as PGF. Myself Dr. Garg, working in the School of Mathematics, Thapar Institute, India. So before we start with the what is the probability generating function, we must understand what is the generating function. So let's say you have the sequence A0, A1, A2 and up to here of the real numbers. Then if you write this in terms of the infinite series, I varies from 0 to infinity, you can see this is the series. So you can say this is my power series, so it must converges over the domain of this R. What is the R is? R is called as the radius of convergence. We will try to find this value of R also depending from the problem to problem. So whenever this series converges, then this AS is called as the generating function of this sequence AI. Make sure that this S is doesn't play any significant role, but it is introduced to identify coefficients of this AI. Whenever you are taking this AI as the probabilities, then we call this generating function as the probability generating functions, like of here. So the probability generating function is defined for the discrete random variable only, which consists of the non-negative values like here. Then the probability generating function PGF is denoted by G of X, and it is defined like here, that is of this. So you can see if you compare this value with respect to the previous slide, that is AI as raised. So this AI is defined in terms of the probability. So when this infinite sum will converges, then only you can say this is the probability generating function. Make sure that the probability generating function is a useful tool for the discrete random variables only. It is not defined for the continuous one. And based on this generating function, that is a G of X, we can define the probability at X is equal to 1, probability at X is equal to 2, probability at others also. So that is, it can use to generate the probabilities of the distributions. How? We will see in this slide, in this presentation also. How you can define the relationship between the probability generating function and the moment generating function. We have seen in our last lectures are how you can define the moment generating function here, and you can see the probability generating function is defined like here. So clearly you can see if I replace the value of the S to be the e raised to power t, again it's a real number which is a real, so you can see it converted to here. So what is the meaning of that? So if you replace the generating S, the parameter S to be the exponential, then it becomes the moment generating function. It means if you have the generating function of any series is like say PS plus Q raised to power n, then the corresponding moment generating function will be, you can simply replace S with the help of small t here. What are the major properties of the generating function? That's very important properties are there, you should remember that. Now first property is that G of 0 is nothing but the probability at X is equal to 0. So if you open this bracket, what will happen? This is nothing but S raised to power 0, X is 0, plus S is 1, probability at X is 1, and so on. So anything power 0 is 1, this is probability at X is equal to 0, plus S, probability at X is equal to 1, plus so on. Now you want to compute the generating function at a 0. So what will happen at S is 0? This becomes a 0, this is 0, the only remaining thing is X is equal to here. So in either you can start from here, S, you can substitute the value of the S as a 0 here, and then once you will open this bracket, now you can see this is the indeterminate form. So how you can do that? You can simply take S raised to power X, and then you can take as X as a 0, firstly take, then it becomes a 1. So it means this value becomes my 1 is there. So this part is my 0, this is 0, this is nothing but here. Second major important property is the generating function at a point 1 is always be a 1. So we can start from here. Now I can open this summation as X is 0 here. What is that? Anything power 0 is 1. So this is here, plus X is equal to 1, plus X is, and so on. What is that? This is nothing but my summation of here. What is that? This is nothing but my PMF. So what is the sum of the PMF? It is nothing but my 1 because it's from a PMF. How you can find the probability generating function for the binomial distribution? So if you have a random variable X whose parameters are n and p, then what is the PMF of the binomial distribution? So all of you know that this is the NCX what is the, this represent my combinations and CXR. Now we can start with the definition of the generating function. G of is here. I can substitute this value here. I can take the pair of the Sx and the Px. So I can write this pair as of this. Now, do you remember that what is the series expansion of this? If you take as an infinite sum, yes, this is a binomial series. So you can see with the help of the binomial, you can see Ps plus Ku of here is the required generating functions of the binomial. If you want to find the moment generating function corresponding to it, what will happen? You can simply replace S to be the e raised to power 2, and you must remember that this is a required moment generating function of here. You can easily verify that whether this will satisfy these two properties or not. You can see what will happen as S is 0. Okay, you can start from here. If you substitute S is 1 here, what is the value of this? It is nothing but my P plus Q, and P plus Q is nothing but my 1. If you start from here, if you take S is 0, what will happen? This is my 0. So this 0 means this is nothing but my Q of n. And what is the Q of n? It is nothing but here in the binomial theorem distribution. So it means these two properties are satisfied. Similarly, we can define the probability density function, generating function for the Poisson distribution here. So what is the PMF of this? So the PMF of this is my here. So I can substitute the limits from 0 to infinity. I can take the value of this as of here. Now I can take, since the summation is start from the x, so I can take this constant, I can take this as a outside and take these two coefficients as a here. Now do you remember that what is the series of this? This is the infinite series. So if you open this, this is nothing but my exponential series. Here is my exponential series for here, and I can write here. So again, you can see that what is the moment generating function corresponding to the Poisson distribution. You can simply replace S with the help of T, and this is the same answer. Again, you can easily verify that whether this property is satisfied or not. You can see whenever S is equal to 1, what will happen? This is my 0, so e raised power 0 is my 1. What will happen if S is 0? So if S is 0, then it becomes my e raised power minus of lambda. You can see what is the value of x is equal to 0. This is nothing but anything power 0 is 1, 0 factorial is nothing but 1, is the same thing. Similarly, we can define the probability density function for the geometric distribution. What is the PMF of the geometric distribution? This is here. Start from x is 1, 2 and so on. Or some books may also be defined as generating function like of this q raised power x of p, provided x start from the 0, 1 and 2 so on. So since I started from the 1 to infinity and it take x minus 1, so you can see the limits is again 1 to infinity. While in the previous cases all are x from the 0 to infinity, because the domain is my 0. Now I can substitute this value here. Now since the limits are start from the x, so what is that? This p is common, so this is q raised to power minus 1. I can take this as a outside, p over q is outside. What is that? This is, so if you open this bracket, what will happen? So this is nothing but the qs, this is q square s square, this is the q cube s cube and so on. So what is that? This is nothing but my geometric series. And what is the sum of the infinite series of the geometric? That is a upon 1 minus r. So I can write this as here. And this is convergent only when the ratio is less than 1, or you can see s is less than 1 by q here. Again, if you want to find the moment generating functions corresponding to them, so it is nothing but my p e raised to power t upon here. Also, you can verify that the g of x of 1 is a 1 or not. You can see when you substitute s is 1, it is the 1 minus p, that is nothing but the p, 1 minus q is p, so it will be cancelled out, and here. Also, you can see g of 0 is nothing but my here. How you can define the probabilities using the PMF or using the PDF? It means you have this probability density function. How you can find the probability at x is 1? How you can find the probability at x is 7 and so on. And that's a very important concept for the CSR, GATE or the other examinations are there. So I assume that I can donate this P of x as here. Then our target is to recover all those probabilities from the PGF. I can expand this in terms of the infinite series. Now you can clearly say that if I take s as a 0, what will happen on the right hand side? This is my P0, this part is my 0, this is my 0, and so on. So what is that? P of 0 is nothing but my here. So what is the meaning of that? If for example, in case of the binomial distribution, you have the PGF of this. Now what is the probability of the binomial distribution at x is 0? It means at 0. So if you substitute 0, it becomes is the required answer. How you can find the probability at x is equal to 1? So you can take the differentiation of this, you can take the partial derivative, you can take the first derivative of this. So this is my here, this is my 0, this is my p1, this is my twice of this, and now again you can take the derivative at a 0. So this becomes my p1, this is 0, this is 0, this is 0r. So what is the p1 r here? That is nothing but my of here. So it means how you can take the moment probability at x is equal to 1 corresponding to the say binomial distribution. So we know that this is my PMF, this is my PGF. Now you can take the first derivative. So what is that? This is nothing but my here n minus 1 of p. Now you can take at s is equal to 0. So whatever the answer of this, when you take s is 0, this is my here. Similarly, if you take the second derivative of this, you can take the second derivative of this, you will get here. Again at s is equal to 0, you will get this. So can you find this value? What is the value of the x is equal to 2? It is nothing but my 1 by 2 second derivative of here. Similarly, you can take the third derivative, you will get this one r here. So it's a 6 it can be written as a 3 factorial and so on. So this 2 I can write as a 2 factorial. This is nothing but my 1 upon 1, I can write as a 1 factorial and so on. So you can see probability at x equal to 0 is nothing but g of x. 1 means the first derivative, 2 means the second derivative, 3 means third derivative. So in general, it is a n means 1 upon n nth derivative. Or you can write as a nth derivative of this at a point s is equal to 0. For example, here, so let's say x is a discrete random variables with the probability density function, generating function is here. You have to find the distribution of the x. That's very simple. You can take the first derivative. This is the target you have to find. So you can take the derivatives are there. The first derivative of this my here. You can take the second derivative, third derivative, and all those fourth derivatives onward are my 0. Now you can compute the values of this at a point 0 because we need the at a 0. So what is the value of this? It's nothing but 0. What is the value of this at a 0? It is nothing but my 2 by 5 and so on. Now you can substitute this value 1 by 1 here. So when you take r is 0, that is what is the x of 0? That is 1 upon 0. 0 factorial is 1 and nothing derivative. So that is this value. What is that? This is nothing but my 0. What is x equal to 1? It means it's a 1 upon 1 factorial. The first derivative of this, what is the first derivative is 2 by 5 is the required answer and so on. So it is a 1 upon 2 factorial is a 0, it's a 1 by 3 factorial. 3 factorial is 6. So 1 by 6 of 18 by 3, that's a 3 by 5 and all others are 0. So what do you conclude from here? That is whenever x is equal to 1, it's a finite answer. X is equal to 3, it's a finite answer. So it means your corresponding probability is my whenever x is 1 and whenever x is 3, you can see it's a 2 by 5, it's a 3 by 5, and you can see that it's a PMF. Why? Because the sum of them is a 1. So you can see the value of the x is 1 and 3 with the probability 2 by 5 and 3 by 5. Can this be the PGF of the random variable x? How you can verify that? You have to take these two properties. Firstly, you have to check whether this is 2 and second one is this is 2 or not. This is my 1. So if you start from here, what is the gx of 0? It is nothing but my 2. So which is, we can first method is here. What is that? Now since this is the probability, can this be greater than 1? No, because probability can't be greater than of the 1. So it means this is not the PGF. If you want to verify this one, what is that? Can it be 1? Yes, it is 2 because it's a 2 upon 1 plus 1. It is 1, that's a 2. But the first, this property is not satisfied. It means this is not the PGF. So it is not PGF. This is the first method. Otherwise, we can start with the definition of this. What is the definition of this is my here, and this value is given to be here. I can write this value as of this form. This value I can write as such. Now, can I expand this with the help of the binomial distribution? Yes, you can see with the help of the binomial theorem here. I can write this, can I write this value as of like here? Depending upon the summations, you can write like 2 is there, this is the alternating sign, this is the GP and here. Now, if you compare this with the help of here, what is the value of this? You can take summation is common, so it means this value. Now, here is a probability, so you can take say p x is equal to 1. What is the value of the x is 1? It's a minus of 2. Since probability can't be less than of the 0, it means this is not possible. Also, if you want to take x is equal to say 2, what is the answer of this? It's a plus of 2, which is a greater than 1. Again, it is not a possible. So it means this cannot be a PGF. Look at one more example are there. So you have the PDF of there. So how you can find the probability at x is 1? So I will tell you the two different methods. This is the first method. So I can write this PDF as of this. I can take negative as a common. So do you remember that any of the distribution whose PGF in the form of the exponential part are there? Yes, this is the Poisson distribution are there. So if you compare them, what is the value of the lambda? It's nothing but 3. So once you know that it's a Poisson distribution, now you can apply the Poisson distribution PMF at x is equal to 1. So you can substitute lambda is 3, you will get here. So this is the first method you can apply. Remember that you have to remember the PGF of the respective distribution. On the other hand, if you know how you can compute x is 1, that is nothing but the 1 factorial and this derivative are here. So you have this, you can take the first derivative of this is the first derivative. Now you can substitute at s is 0. So what is the value of the s is 0? You can see these are the same as before. So you can choose any of the methods. Look at again here, if given to you that the PGF of the x is given to here, you have to find the PGF of the x minus a upon b. So that's very simple. You can start from here, that is I can replace this value of here. Now I can take it separate. Since this expected value which are varying with respect to the x, so this part is my constant, so I can take this as the outside. Why? Because expected value of this is nothing but a times of here, so I can take it here. Now I can compare this with the help of this. I can see s is nothing but my 1 on b, so it means this is my PGF of this. Similarly, you can find the PGF of the x plus 1 and of 2x if you know the PGF of the x. How you can do that? You can start from here, that is x of here. I can take it as a separate. So how you can write that this is x of this. Now since this is a independent of the x, I can take it as a outside. This is my here. So what is that? This is nothing but my PGF of the r here. Similarly for here, you can start from this. This is my 2x. Now if you compare this value, I can write this as s square of the s. What is that? This is nothing but my here. So this is the way you can solve these PGF distributions R. We will see in our future also how you can find the mean are there, but one of the most important result is the uniqueness of here. We have seen that how you can compute the probabilities with the help of the PGF, that is in the help of the derivatives. Now this PGF uniquely specifies the set of the probabilities. What is the meaning of that is, so it means if you have the two different power series which contains some radius of convergence having a 0 however small, then all the series are equal. What is the meaning of that? It means if you have the two different power series A and B, which can be written like here, such that they have the common radius of convergence R, such that A of s and the B of s are same, provided this radius of convergence hold, then this coefficient, that is a generating series, sequences are always be same. Or you can say it can be shown that if you have the two random variables having the same PGF, then the two random variables have the same distribution functions. So that's the meaning of the uniqueness of this PGF. We will see how you can compute the mean and the variance from the PGF, as we have discussed in here how you can compute the probabilities from the PGF. Now we will see how you can compute the mean and variance from the PGF in our next class. Till then, you can simply like, share and comments on this video. You can see more updates on this channel named Dr. Harish available at here. Best of luck, students. Happy luck.